ratios were like, how are we and yet nobody, most particularly Chandra, sort of realized what this was trying to do.
But what she did was,
Well, I want to begin by telling you Randy Gallistel story. I was asked to return to give a colloquium, so I've used this before at Penn when Randy was still there. I think I was at Harvard. And I was asked to say something about Randy in the beginning of the talk, and so I thought I would just repeat that here. It's quick. I characterized Randy as coming out of that book by Douglas Adams. I think it's The Restaurant at the End of the Universe. If you remember that book, in that book, laboratory rats in psychology departments are astral projections from a different race that is working to help the Earth, which is a giant organic computer, which is trying to solve the question of what is the meaning of life and everything, which they have been unable to solve. They built the Earth as a computer, and they fine-tune it by throwing the results of the psychology experiments by managing these astral projections, which we call rats. And we graduate students decided that Randy was an astral projection. And it explained two important behaviors that otherwise were unexplainable. It explained the pauses that would happen in the conversation. And that was because something was happening on the home planet. And he couldn't quite manage it. And he would freeze. And the other thing it explained is why he knew everything.
Welcome back from lunch. I hope you all had a chance to continue doing what we've started doing today, talking with friends and colleagues, telling good stories. Our next speaker is Elizabeth Brannon. She's professor of cognitive neuroscience and psychology at Duke University. While she is not a direct academic child of Rochel and Randy, I think you'll agree she is the perfect example of what their perfect academic child would be. Liz got her BA at Penn, but it was ARR, after Rochel and Randy. And it was in anthropology, but we won't worry about that. She then got her PhD at Columbia and combines anthropology, psychology, neuroscience. She studies the development and evolution of quantitative cognition, focusing on behavioral and neural underpinnings of adult human mathematical cognition, the precursors of these abilities in infants, and their evolutionary basis in non-human primates. How could you think of a more appropriate combination to celebrate your two intellectual traditions? And I was going to say a couple of words that Liz had written about how she met Randy and Rochel, but I think I will leave that to you. Yes.
Okay, thanks. It is just so wonderful to be here. It is really an honor to be part of this and to pay tribute to both of you, Brannon and Rochel, who have had such a huge influence on my research program, as I will show you today. So, as we've been hearing, the study of numerical cognition is really a remarkable test bed for understanding both the evolution and the development of the mind. And my work is on both of those topics, and the thesis that I typically use to integrate all of the work that I present when I give talks is that the approximate number system is foundational for mathematics. And this is by no means an original thesis, although it is controversial. It's not at all original. And so in this quote by Brannon and Rochel, they suggest that the foundations of human numerical competence lie in pre-verbal mechanisms for counting and arithmetic reasoning that we share with genera at least as distant as rodents and birds. Now, as Mary said, I never worked directly with Randy or Rochel as their student. But let's go back to the year 1997 or 1998. I'm not quite sure which year. I was a graduate student at Columbia, and my husband, Michael Platt, was a postdoc at NYU, and Randy and Rochel were on leave at Rutgers. I was a student of animal cognition at Columbia, so I was working with Herb Terrace and also with Pierre Balsam and John Gibbon, taking classes with them, studying animal cognition. Michael was working with Paul Glimsher, who was a graduate student previously with Paul, or postdoc, not sure which. Anyway, so you can imagine there were many potential ways in which I could have met Randy and Rochel, and should have met Randy and Rochel. But I didn't meet them originally through any of these connections. Instead, I met them because I lived in number 2 Washington Square Village at NYU, and I walked my dog in Washington Square Park. So, sorry, Kim, have a little dog connection here too. And this is not Foxy and Biscotti, but unfortunately I don't have any pictures of them together. But I met Randy and Rochel walking my dog, and my memory of it is that our dogs were starting to communicate, and Randy said something like, I'm Randy, and I said, yes, I know, because of course Michael and I had already been kind of spying on them for quite a while. They actually lived on our floor, and we'd been seeing them in the elevator, but we were kind of too shy to say who we were. And so we already were very familiar with all of their work, and we're thrilled to start getting to talk to them. And then the best part of this whole scenario is that they went away somewhere, maybe Paris, and left Biscotti with us. And so we took care of their dog, and the best part of that is that when they got back, they took us out to dinner to thank us, and we had this wonderful dinner, the 4 of us, that ended up having a very big influence on my life. So my memory of that is that Randy said something like, so Liz, what are your dissertation plans at dinner? And so I pitched him my dissertation plans. Pitched both of them my projected study, which was all on how monkeys see the world with categorization, in terms of categorization. So what kinds of natural categories do monkeys have? The difference between artificial and natural categories. I was going to adapt Herb Terrace's, my dissertation advisor's, paradigm, a simultaneous changing paradigm, and train monkeys to respond to particular categories and then see whether they transferred to new exemplars of the same category. And Randy and Rochel kind of listened politely and said, oh, that sounds very interesting, but it would be much more interesting if you did that with number. So that kind of changed everything, I think, and influenced me a lot, and ended up in many ways moving towards this, my dissertation study, which was exactly what I just described for categories, but based on numerical categories. So here are some examples on the left of a monkey from that study doing a simultaneous chain based on number. And this is a transfer test where the monkey has been trained with the values 1 through 4 on the left and is now being tested in pairs and getting reinforced with food. On the right, you can see a monkey getting reinforced with juice, also ordering numerical values. So this is the kind of data you get from these paradigms when monkeys are asked to make these judgments. We see that both accuracy and reaction time are modulated by the ratio between the 2 numerical values. So Weber's law applies to numerical judgments, and we've seen previous examples of this in Brian's talk. And in fact, we see that monkeys show this ratio dependence, and college students tested in the exact same task show very similar performance. So this, similar to what Ryan showed you for fish and humans, and similar to what Randy and Rochel did with Balin and with Sarah Cortez as well, replicating a study by Platt and Johnson with rats and showing that number production tasks show scalar variability in humans and very similar performance in animals and humans. While still a graduate student, I was reading the seminal paper by Randy and Rochel in Cognition alongside another paper published in the same volume by Stan DeHaan, where they have a very spirited disagreement on the subjective representation of number. And Stan talks about number as being logarithmically compressed, as Brian referred to, The idea that in subjective space, numbers are getting closer and closer together, and that's why we see these distance and magnitude effects. In contrast, Randy and Rochel, in their paper, argued that number is represented linearly, and that the reason we see these distance and magnitude effects is that the variability is actually increasing in the representation, and it is scalar, so it's increasing linearly with number. So I was reading these papers and discussing them with John Gibbon, and he, and of course it's written in Randy and Rochel's paper, the seminal study by Gibbon and Church on how they thought they had differentiated these two ideas for the representation of time. The idea of logarithmic versus linear with scalar variance representations for duration, for time. So they had created this brilliant time-left paradigm where they used subtraction to try and get at this. And so this is the only time that I've directly worked with either of them, where from afar, Randy was already gone by this point, but Randy collaborated with me and John, another student, to adapt that time-left paradigm to try and ask this question about number representation. And I think we believe that we solved the problem, but not everybody does. That number is represented linearly with scalar variance. Okay, so the thesis that the approximate number system is foundational for mathematics, what I'm going to do in the rest of the talk is first talk about the approximate number system itself and describe different aspects of it, and then move on to what I think is the evidence that it actually is foundational, the empirical evidence at this point that it is foundational for mathematics. So, as Randy wrote, only if the brain brings combinatorial processes to bear on the neural entities that represent numerosities, may we say that the brain represents number in an interesting sense of the term representation. So the idea is, well, what is number used for? It's not interesting to talk about number representation unless number is being entered into arithmetic computations, unless it's actually useful and doing work. And so that's one of the, that was an inspiration to do for many studies, and here's one example. This was part of Jessica Cantlin's dissertation work, and on the left, okay, you're seeing 2 plus 2 is 4. Here you're going to see a monkey, whoops, we don't need sound for this one, flexibly going back and forth between addition and subtraction. So 6 dots minus 4 dots is 2 dots. 1 plus 1 is 2, so you can see there's no cue as to whether it's addition or subtraction. She's just supposed to keep track of the number of dots that are behind that green includer. And of course, she's not seeing the little Arabic numerals, those are for you. So I think this video shows you that monkeys are able to keep track of the number of individuals behind these occluders. And in fact, the data suggest that they're not doing this by tracking individual objects. They're doing this using approximate number representations. So these are 2 different monkeys, and in both cases you're looking at accuracy as a function of the ratio between the correct answer, the sum or the difference, and some different value, some distractor. And you can see that it's the ratio between the correct answer and the distractor that controls their performance. And in fact, it doesn't matter whether the distractor is larger or smaller than the sum, that's the little inset figure there. And it also doesn't matter the 2 different lines on that graph are novel and familiar values. So when we train monkeys with particular numerical exemplars, we then test them with new values, and you can see that the monkeys are just as proficient with new problems as they are with the trained values. So they're keeping track of these approximate representations, and the fact that it's ratio dependent is showing you that the representations are approximate and not precise, and that they're following Paper's law. In more recent work, we've been asking the question of multiplication, and this is something that Randy's addressed in other studies with Matt Leon, I believe. This is based on a question of whether monkeys can make an inference about what's under different occluders. So the basic idea is that they learn that there's always the same number of items under each occluder. and we only show them what's under 1, and the question is whether they can then do something akin to multiplication or repeated addition. So we change the number of occluders, we change the number of items under each occluder on different trials, and in general, what we see is that when we train them with other values, these are non-differentially reinforced probe trials with either 3 or, 3 or 2 operands, we see transfer to the novel values. Brian also mentioned the question of, or pointed out that number is unique in the sense that it's abstract. And that is another hallmark of approximate number representations, that they can be cross-modal. So here, you're listening to a sequence of sounds. The monkey's job is to keep track of the number of sounds that she hears, and to then choose the array that numerically matches the number of sounds she has just heard. So in this task, we actually see that monkeys are just as good at matching across sensory modalities, the number of sounds they hear, as the number of visual items that they see sequentially to a visual array. And in fact, again, on the right, the data is plotted as a function of the ratio between the correct answer and the distractor, and you can see that that's what controls performance. So we're seeing this ratio-dependent performance and cross-modal matching. So I'm now going to turn to the developmental story of the hallmarks of the approximate number system. And the main task that's been used is the visual habituation procedure, where infants see repeatedly different images that have the same number of items, and then are shown new pictures that either have the same number or a novel number of items. And there had been quite a lot of work using this procedure, which suggested that infants represent number. But as Brian was criticizing, some of the stimulus controls were a little weak in the early work. But Feishu and Gallistel used a much more stringent stimulus control design and showed that babies at only 6 months of age could discriminate 8 from 16 dots. So by varying both intensive and extensive stimulus parameters, so aspects of individual elements within the arrays and cumulative aspects of the array, they were able to show that infants could make these discriminations when the ratio was favorable enough. So infants could discriminate 8 versus 16, but not, for example, 8 versus 12. But that's quite different from the kinds of psychophysical functions that we can see with animals and with humans, tested in explicit tasks where they can use touch screens or other kinds of responses where we can look at accuracy and reaction time. And one thing that Rochel always emphasized when I would talk to her about starting to do work with infants is that we need measures that give variability and individual measures that can tell us differences about individual children and trial-to-trial variability. And that's lacking in the infant literature in general. So that was a goal for a long time. We tried many different ways of coming up with infant measures that would give us that kind of variability, unsuccessfully. But Melissa Libertas, as a graduate student in my lab, came up with a task that is that gets close to that has some of those features. So she adapted a paradigm that Lisa Oakes and her students had used to study short-term memory to look at numerical change detection. So rather than describing that slide, I'll show you what it looks like with an infant. So this is an attractor stimulus. The infant is just looking at that straight ahead. And now before you look up at the stimuli, just watch the baby's eyes. So he's clearly evaluating both of these streams of images, but now he is fixating on one of them. And I think you can see that the one that he's fixing on is changing numerically. It's alternating between 10 and 20 dots. Whereas the one that he has given up on is a constant 10 dots. So what we see in this task is that infants like to look at the numerically changing stream. And what's great about the task is that we actually see that the preference scores are modulated by the ratio between the two values in the changing stream. So these are 4 different groups of babies, And the group on the far left is looking at a 2 to 3 ratio change in one of the streams and it's constant in the other. And that group of babies is not showing a preference to either stream. In contrast, the group all the way on the right is seeing a whopping 1 to 4 ratio change in one of these streams. And of course, between trials, the left-right location is changing for the infant. So we see that the preference scores are actually increasing with the ratio in the changing stream. And we see variability in the individual infant scores. So this shows you that there's lots of variability. These are the individual infant scores. And it also shows you that there's some predictive power of 6-month scores on the x-axis for 9-month scores. So 3 months later, there's some predictive power of the preference scores at 6 months for their scores 9 months later. So part of the goal here for this task was to get a measure in infancy that could give us this individual variability. So I'll return to this later. Another bridge and gift that Rochel and Randy gave me is Sarah Cordes. So she was a graduate student with them and came to do her postdoc with me. And while she was working with me, she addressed these really important questions about the relative salience of surface area and number in infancy. So in both the developmental literature and the animal literature, there was this prevailing idea that surface area and other continuous aspects of a stimulus array are much more directly perceived, much simpler to represent than number. And that was something that Randy and Rochel argued with in their writings. And in the animal literature, it was referred to as the last resort hypothesis, the idea that an animal would only represent number if it was a last resort, if they were trained for thousands and thousands of trials and showed that everything else was not going to get them reinforcement, and that this was the only avenue to reinforcement. And in the infant literature, of course, even beginning with Piaget, there was also this notion that surface area and continuous variables were more salient and simpler for an infant. And so Sarah, in many different studies, challenged that idea and asked how we can compare the psychophysics of infant area and number discrimination. So the very basics, first of all, we need to know, can infants discriminate based on area? So this is just a very simple basic study which shows that infants can, in fact, if they're habituated to a small Elmo here, show a novelty response when Elmo, I believe, is about to quadruple in size. Okay, so the infant hasn't seen it yet, but as soon as he does, he's looking at his mom now, but now he is mesmerized by this, blowing up of Elmo. And in fact, it works in the other direction as well. If Elmo shrinks, they're still captivated by it. And interestingly, babies need a 1 to 2 ratio for area discrimination, just like numerical discrimination at 6 months of age. So Sarah went on to ask questions about arrays of objects. So although it looks like the threshold for discrimination is similar for a single item, what about this assumption that babies can actually sum over lots of individual elements, and that that's a simpler thing to do than to abstract a number from a stimulus? So what she did was to ask whether, well, if we vary number in habituation but keep cumulative surface area constant, will babies dishabituate in the same way to a novel cumulative surface area that's, let's say, the average of the numerical values that they were habituated to? So this is a little bit, I won't take you through all the details of this, but on the left, this would be for small values, and on the right, it would be for large values. And in both cases, the idea, if we go over, let's say, just for the small value one, the idea is that the stimuli would be 2 or 3 in habituation, and that in this case, in test, there would be a single element that was either the same cumulative surface area or 1 to 3 ratio change, either smaller or larger than the cumulative surface area that they're for large values. And what Sarah showed in a series of different studies is that infants actually were much less sensitive to cumulative surface area than numerosity. So for cumulative surface area, infants seem to need a 1 to 4 ratio change, whereas for number at the same age, 6-month-olds, could do any of these ratios, 1 to 2, 1 to 3, or 1 to 4. So there's also been quite a lot of work on the neural basis of number representation in humans, and more recently, a growing body of work in animals and children. And Brian referred to some of this, and his own work, of course, on patient work, showing the importance of regions such as the interparietal region. And it appears that this region is very important early in development, again, pointing to the idea that it is homology that we're looking at, that it's the same system very early in childhood, and even in infancy, before children know the meaning of number words, that the interparietal sulcus is representing number non-symbolically. And in fact, it looks like in monkeys, that the homologous brain region shows neurons that are sensitive to number in different ways. And I'm not going to go into the details of all of that, but I want to just briefly do an interim summary of the different aspects of the approximate number system that I've described, and then move on to this basic question about whether it is foundational for higher level math. So I've shown you that it's shared by other animals, and that it's there in early infancy. That it shows ratio dependence, that it continues to function even after more elaborate conceptual structures emerge. So this is a feature of core knowledge that Liz Felke will talk more about, and that clearly exemplifies the number domain. So the fact that we see adult humans and monkeys performing the same way, and rats and fish in various tasks where we can test animals and humans in the same task, the fact that we can strip away all of that is influenced by culture and symbolic number representations and still see the same kinds of performance. These representations support computations, and they're abstract in that they're cross-modal. And most generally, they are fundamental and primary for animals and infants, so they seem to be more salient even than other dimensions in Sarah Cortez's work, for example. And there is specialized neural circuitry, or at least homologous neural circuitry, throughout development and in primates. Okay, so moving on to this question of, okay, what is this approximate number system for? Is it in parallel to what's uniquely human in mathematics, or is it foundational for it? So these are the different pieces of evidence that I want to focus on to differing degrees. So the first is that the approximate number system acuity of this system correlates with symbolic and math ability. So this is a growing literature that started with a study by Justin Hilberta, Michelle Zotbo, and Lisa Feigenson not too long ago, in 2008, that kind of gave us evidence for what we were assuming, but there wasn't any really direct evidence for this. The idea that variability in our ability to make these nonverbal numerical discriminations is actually linked to symbolic arithmetic. So in this study, they had access to a longitudinal database of children who had gone through various standardized tests, including 2 different math assessments, the Woodcock-Johnson calculation portion and the test of early mathematical achievement. And they had been tested on these 2 assays every year from age 5 to age 14. And so what the group did was to then measure Weber fraction in these 14-year-olds. So measure the acuity of their nonverbal numerical system, their approximate number system. And what they found is that the Weber fraction predicted both of these measures, and actually that was true throughout the data set, so all the way down to 5 years of age. There have been many studies at this point using different dependent measures, whether there's some using accuracy rather than Weber fraction that may account for some of the discrepancies. And there's some using different measures of symbolic mathematics. And there's a little bit of a controversy about whether this holds, but in general, I think that there's quite a lot of evidence suggesting that this link is actually there. And in fact, a recent meta-analysis suggests that indeed it is. And I won't talk about this because Brian would be in a much better position to talk more about this, but there is also clear evidence of that this system is implicated in dyscalculia. So that dyscalculia is domain-specific for number, as we talked about. So this is further evidence for this idea. And the third piece of evidence that I want to talk about is data from our lab that suggests that infant numerical discrimination is actually predictive of later math ability. So back to the individual variability question and this change detection procedure that I showed you, we wanted to ask the question of whether infant scores at 6 months of age would predict symbolic math ability later. So I described the task to you on the top. Now on the bottom, this is a design, this is the longitudinal design that we used. And in the initial data set, this was an opportunistic longitudinal design, so I'll get back to that. So we measured ANS acuity and perceptual discrimination ability using the change detection task. So either using numerical stimuli or non-numerical stimuli and this change detection task in infancy. And then 3 years later, we brought the children back to the lab and measured their vapor fraction using a touchscreen task, measured their math ability using the test of early mathematical achievement, measured their counting knowledge using the given number task, and measuring IQ using the RuCCS. And the prediction was that the infant scores would account for some of the variance in both the vapor fraction and the test of early mathematical achievement, and not in the other measures. So let's just think about the first one, whether infant numerical acuity predicts vapor fraction. That, of course, is the underlying assumption of all of this research, right? That what we're actually measuring in infancy using looking time is numerical discrimination ability. And so if there is consistency, of course, there's a question as to whether there should be any consistency over 3 years of age, and given the amazing kind of noise that we see in infant data in general, but it's certainly, the prediction would be that the infant scores would predict vapor fraction. But then asking this question of whether the non-symbolic, non-verbal system for representing number is predictive of the test of early mathematical achievement is getting at this question of whether the non-verbal system is actually linked to mathematics. So what we found in our first sample, which was, as I said, an opportunistic sample, so we had already had these infants in for cross-sectional studies, and we recruited as many of them back as we could, was that in fact the infant vapor fraction on the x-axis did predict a significant portion of the variance in the children's vapor fraction scores 3 years later. So this was exciting. This suggests that we actually are measuring vapor fraction in infancy using this change detection procedure. And in fact, we also found that a significant portion of the variance was explained in the test of early mathematical achievement. Now, in both cases, it's a small amount of the variance that is explained, and it's clear you would imagine that there should be many, many things influencing both of these, both vapor fraction and symbolic math ability. Certainly, things like what kind of preschool input they're having that Kim talked about, and what kind of math talk at home, and many, many different things are going to be influencing their performance on the test of early mathematical achievement. But the fact that it's accounting for any of the variance in these two measures is interesting and consistent with the idea that there is this important relationship between the two. The fourth piece of evidence that I want to offer is a recent study that we did using EEG that suggests that ANS representations are actually linked to number word representations before children are actually showing clear evidence of being cardinal principle knowers. So this is a study that postdoc in the lab, Michal Pinhas, did, and she adapted studies that were used to look at the neural basis of word learning that were non-numerical word learning by Angelica Frederici and others. So there's very little literature in general on the neural basis of children's numerical abilities, But to my knowledge, there are no studies that are looking at the neural basis of number word knowledge. So normally, either we're looking at dot arrays or symbols visually, and not the neural basis of number words. And yet, of course, children learn the meaning of number words before they learn the meaning of Arabic numerals. And there's lots of debate about what they're actually mapping these number words onto. So we hoped that this study would shed some light on that. So basically, children heard a word like look, 3, and they saw a visual array that either matched the number that they were hearing or was incongruent with the number, that word that they were hearing. And these were 3 to 5-year-old children, so some of them would pass the given number assay and show evidence being cardinal principal knowers, and some of them would fail that assay and be subset knowers. So we used EEG with these children, and as I said, we also, on the right, used the given number task. And what we found is that there were 2 different ERP components that we're calling the NINC and the PINC. So a negative polarity incongruency response and a positive polarity incongruency response. Both of these components differentiated congruent and incongruent trials. So when the child heard a word that was congruent with the number of objects they were seeing, and when they heard a word that was incongruent with the number of objects they were seeing, these 2 different components, in fact, differentiated that. However, the PINC, the later one, this bilateral parietal component that was between 700 and 1,000 milliseconds, showed a graded ERP response as a function of distance. So depending on whether the visual array was more numerically different from the word that they were hearing or more numerically similar. So if you look at the bottom right inset there, you can see that the mean amplitude with negative plotted up, it's more negative for the 2 to 3 ratio than the 1 to 3 ratio, for example, more positive for the 1 to 3 ratio. And what was really interesting about this is that this was true in children who were subset knowers. So this data is for the subset knowers. So it's not that surprising that it would be true in children that really understood the meaning of all of the number words, but it was true even for children that only understood partially, based on that assessment anyway, the meaning of the number words. So this provides some evidence that children are actually mapping approximate number representations onto number words before they've necessarily grasped the meaning of all of the number words or mapped the meaning of all of the number words. And so while it's not necessarily evidence that the approximate number system is doing all the work in helping children learn the meaning of number words, it's certainly suggested that it's happening earlier than some accounts, like Susan Carey's bootstrapping hypothesis. And there's other behavioral data that I'm not sure that maybe Liz Spelke will talk about that also suggests this earlier mapping of ANS representations onto number words. Okay, so the final piece of the puzzle that I want to talk about is getting at this question of whether there is a causal relationship between the approximate number system and math. So everything I've talked about up until now on this list is correlational. And so the final question that we have been addressing lately is whether we can find any evidence that this is actually a causal relationship. So we've been doing this through training studies. So this is Jude Coupart, who was a postdoc in the lab and is now an assistant professor at UMass Amherst. And he used this pre-post-test training design. So he gave college students, this first study was with adults, a pre-test of a symbolic math assessment, very simple, 2 and 3 digit and 2 and 3 operand addition and subtraction. How many problems can they do correctly within 2 5-minute blocks? And a vocabulary assessment, seemingly would have nothing to do with approximate arithmetic. He then had half the subjects do an approximate arithmetic training, and I'll show you what that looked like, or in this very first study, just a no-contact control. So they did not come back to the lab during those 10 training days. And then the post-test was identical to the pre-test. So the question is whether training to improve the approximate number system would actually have any effect on symbolic mathematics. If there is this causal link, then it might actually improve symbolic arithmetic. So here's what it looked like for adults. They see a dot array go behind an includer, another dot array, and now which one is the sum? One dot array behind the includer, another. Now, is it more or less than that array? So it's quite challenging. Subtraction match. So they see an array, and they see another array leave from behind the includer. Is it this or that? Which one's the difference? And the same thing for subtraction and comparison. So that minus that, is it more or less than that array? So it kind of keeps you on your feet. You've got these 4 different tries. The task is titrated, so it's getting more and more difficult as you're getting better and better at the task. And the subjects are coming back in this first study 10 different times for half an hour each. And what we see is that, first of all, performance is improving over the 10 sessions, although it seems to reach kind of asymptotic performance for this window, at least pretty early on. But the log difference between the correct and the distractor is decreasing, showing that they're getting better at the task over time. But the important question is the pre- and post-test assessments. So we predicted, of course, that symbolic arithmetic would improve, but that vocabulary would have no effect on vocabulary. And that is what we found. So here you see in gray the approximate arithmetic training condition, and then in the open bars is the no contact control. And on the left is the math assessment, and on the right is the vocabulary assessment. And these are standardized gain scores. So positive bars mean that they performed better on the post-test compared to the pre-test. So as you can see, it's only the approximate arithmetic training condition that showed this benefit in symbolic arithmetic. So what we have done since then are many different studies, some in this paper as well, and others in another paper, that did many different training conditions. So we're attempting to kind of dissect what are the components of this approximate arithmetic task. So as you look at these dots moving around, I'm sure you have many hypotheses of what we might be training. And the one that's kind of most obvious is working memory, right? You have to hold these dot arrays in working memory. So we've been trying to come up with various different training conditions and compare them to this approximate arithmetic condition, and also to use many different post-test and pre-test measures. So here's one example. You might think that ordering numerical symbols, training to do this so that you became more proficient, that these became retrieved more automatically, might in fact be more influential on symbolic arithmetic than approximate dot arithmetic. So in this task, subjects had to use a mouse and very quickly indicate whether 3 digits were in the ascending or descending order. And on the top, those were moving to the left, and so I think those had to be in ascending order, and the ones moving to the right had to be in descending order, and the subjects had to very quickly catch them before they left the screen and get them into the right order. So every time they clicked, they would randomly shuffle the order of the Arabic numerals. And subjects did, in fact, get better at this task when they were trained over 6 to 10 sessions of this. But in fact, we saw no benefit on symbolic arithmetic. So here we've got 3 different training conditions. So instead of a no contact control, we've got knowledge training. So multiple choice knowledge training that should have no effect on mathematics, and numeral ordering training that I just showed you, and the approximate arithmetic training. And you can see that the approximate arithmetic training had a much bigger effect than the other 2. And of course, there may be a test-retest effect in some of these conditions. But not surprisingly, the numeral order judgment did improve another version of ordering numerals. Okay, so we have been trying to extend this research with adults, looking at the causal relationship to preschoolers. So another link to the real world. We've been asking whether we can do this kind of training with preschoolers who are very early in their number word knowledge. So we've gone into state-funded preschools in North Carolina and done the first version of this with an iPad app. And you can imagine that this clearly has very little actual practical applications for college students. But for preschoolers, it is certainly possible that this kind of approximate arithmetic training could be beneficial. So the number sense training game that we created is just a direct adaptation of the adult version that I showed you, and we compared this to a picture memory training game. So here's what...
Okay. Pop the red balloon. The palm trees are going into the box. More palm trees are going into the box. Touch the one that has more. You're correct. Pop the red balloon. Look, some chickens are going into the box.
Okay, so this is the same idea with addition and subtraction and compare and match trials, but more suited for preschoolers. And in this first sample of children, as I said, we compared it to a memory game, also done on the iPad. And we found basically the same pattern of results. So on the left, you can see that the children who played the approximate arithmetic game showed more of a gain in the test of early mathematical achievement than the children in the open bars who played the picture memory game. And on the right, you see the opposite pattern for a short-term memory assessment when the children played the picture memory game for these 10 sessions. And in fact, now there are a number of other studies, one of them by Liz Spelke and Dan Hyde that she may talk about, that support the same idea. And this one's already published. This is in slightly older children, which also suggests that this kind of training actually improves mathematics. So showing this link between the approximate arithmetic system and symbolic arithmetic. And there are a number of other studies that are out there that I'm aware of as well that are consistent. So I've offered you these various sources of evidence that the approximate number system is foundational for higher level math, as Randy and Rochel have hypothesized. And I think it's still an open question as to how this kind of training is actually working. So what is the mechanism? It makes sense that the approximate number system is foundational, but how is this change in the system actually influencing symbolic mathematics? What is the mechanism? So one possibility is that training is actually sharpening A&S representations, that we're actually seeing a narrowing of these Gaussian functions, so a reduction in the noise in the representation underlying different numerical values. This is possible. Another possibility is that training is actually building on the fundamental overlap in the cognitive algorithms that are used for non-symbolic and symbolic arithmetic. So this is something I think is probably true, but it's vague, and we need to pinpoint what this really means in terms of what training is doing. And so we're doing, and I'd love to hear your ideas of how to tackle this. We're moving at this in various different directions. One of them is to look at how the brain changes as a function of this kind of approximate arithmetic training. So to conclude, there's a lot more I can say. I think that what's most fundamental is that the story that's emerging is one that directly comes from many of the predictions that Randy and Rochel have made throughout their writings and career, of a story of evolutionary and developmental continuity. And there's a lot more to learn and find out, and when I don't know what to do next in an experiment, or when a student needs an idea, I often tell them to reread Randy and Rochel's papers, because that's how I determined or came up with the seeds of inspiration for many of the studies that have formed my career. So thanks to all of the students who participated in this, and specifically and most fundamentally to Randy and Rochel for inspiring all of it. Thank you.
Thank you for a really amazing and inspirational story, and I think we have time for questions. 2 minutes.
Great talk. I
Thanks,
really enjoyed this.
So I would have bet, I did bet a lot against the approximate number system having an effect on later matchability and so forth. So I found the original Howard L. paper astonishing, and this work is really amazing. And so I'm, as you said at the end, would have been, just going over what could be the mechanism. So one of the things, I don't know if it could be relevant for these tests or not, but one of the things I thought about was for error detection and correction, that you could have a sense that your answer doesn't make sense. And that would then let you go back and refine your ability. So do you think that's a possible, what might play a role here?
Right, grounding the system and being aware when you've made kind of orders of magnitude errors. Definitely, I think so. And there could be ways of trying to look at error analyses and possibly even doing things like multiple choice instead of, like right now they're actually typing in the answer. And so we won't know if they originally made an error and then corrected themselves very quickly. But if we did multiple choice assessments where we could get those order of magnitude errors, that could potentially give us some insight into this. So yes, I think that's definitely a potential explanation for the link between the approximate number system and symbolic mathematics. I don't know that it explains the training effect, or how it would explain the training effect exactly.
Well, if you're doing bidirectional mapping, it would, right?
Right.
So having the word first map, but then not back, so that it's going in both directions, the training effect is, will make everything more precise. And that must be
Yeah.
One of the interesting connections in this literature on counting has been with compounds and mass nouns has been to quantity. We have an approximate quantity system for juice and the size of chocolate cake piece and things like that. Would you expect it? Do you think that's a similar system or a different system?
So yeah, that's a great question. So in terms of there's lots of work on the overlap of different quantity representations and asking about whether the neural basis is the same, whether there's transfer from numerical training to other kinds of quantity discriminations. And in general, there's lots of evidence for links between them, but also some surprising failures of links between them. So I think that there's no question that in adults, at some point, they're all mapped together in terms of words like more and less, and that there's lots of analogical reasoning about the overlap between different quantities. But in terms of how profound that overlap is in terms of the neural basis, so in Brian's talk, he referred to the Neck and Church model, which was heavily used by Brannon and Rochel in their work and formulation of the representation. And there, the idea is that time and number are actually represented in the exact same neural currency, right? And so I think there's still a lot of work to be done on those questions of how deep the overlapping representations are. But certainly in adult humans, we come to represent different quantities in overlapping ways, yeah.
Is it foundational and then dispensed with, or does it continue to operate afterwards?
Well, so I think that would have been an early hypothesis of mine. I think that it was foundational and that it was no longer relevant later on, but I think all of this work shows us in college students it's still having an effect, right? So training the approximate number system is having an effect even in college students, and this link seems to be potentially stronger in young children, the correlation between approximate number acuity and symbolic mathematics, but it's still there in adults. So Justin Hilberta has this online data set of 10,000 individuals, and we see it over the entire lifespan.
So do you ever get any dissociation between them and patients with neurological damage, so that they're, let's say, their approximate number system, they can't do that, but they can do the nice things that
Yes.
Brian mentioned,
Right.
and vice versa?
Absolutely. So I haven't worked on this, but there's beautiful work by Brian, by Stan DeHaan. Liz has been part of some of these patient studies as well that show these beautiful dissociations between approximate and precise calculations.
So that means that it isn't necessary.
Okay.
So that's what I'm trying to
Right.
get at. If it's necessary, then damaging one should affect the other. If they're dissociable, then it could be foundational, but it's not needed.
I see what you're saying. Okay, I didn't quite know what you meant by needed.
No, that's what I was
I think
saying.
they're linked throughout the lifespan. And so one possibility, for example, is that that functional connectivity between regions that represent symbolic number and are important for calculations and approximate arithmetic is being strengthened in this kind of training, and that there are these connections, but they can be severed. So, right, so you can see these dissociations, and so that certainly means there can be independent, but in the normal adult, they're linked. Yeah.
What task is used with college students?
In this case,
Just in general. Are they addition, subtraction kinds of things?
right, so these were 2- and 3-digit addition and subtraction as the pre and post test. Yeah.
But then that's not, quote, mathematics.
Ah, right. Okay, so I'm using that term, good point. I mean, I'm using that term mathematics to operationally defined as arithmetic, symbolic arithmetic, and absolutely you could take issue with that completely and totally. So I would say, right, the A&S has nothing to do with real algebra or real mathematics. Yeah, right, sorry.
I have to know.
Loose terminology. Yeah, right.
Can I try out a hypothesis with you? One that I'm afraid was rejected by my co-authors on a recent paper. I'm looking for independent support here. So, what we did with a very large sample of individuals is we did a number of visual tasks. Not quite in the way that you described. It was a kind of a different kind of psychophysical task where you had to match by varying parameter a particular target. And so, for example, the target could be the orientation of objects in one panel. You had to match the orientation in your panel, or it could be and so on. So about 3 or 4 of these visual tasks, and including density. What we found was that all of these tasks correlated with people's math scores. So what we thought was, well, one of my hypothesis was that anything that says your parietal lobe is working well is going to relate to any other task that your parietal lobe might do. So if you're very good at these dorsal stream type tasks, then you're also going to be good at math. So it was a kind of very crude, if you like, naive neuroanatomical hypothesis. So this kind of gets round, if you like, the cognitive issue about how the approximate system actually links up with the exact system that we use for arithmetic. It just says, well, it's just the parietal lobe. What you're doing in your training studies is you're actually tuning up the parietal lobe, and so everything else that the parietal lobe does is good. So there is some mention of this in the paper, but my colleagues who are all psychophysicists don't really like it.
Okay.
I just wanted your
It's fascinating. So I think that is something that we really need many more control tasks in all of these correlational studies to figure that out. We have some data that would argue against that, but I think it's definitely, I'm still open to that possibility. So for example, when we train in adults, college students, to just make approximate number judgments themselves, just comparison, we actually don't get the effect. So when we try to tune the A&S by just making ordinal numerical judgments, we actually don't see much improvement over time, and we also don't see this transfer effect. So that would suggest that it's more fundamental to the overlap in the arithmetic operation.
Yeah.
But I'm not wedded to that. I mean, I think that it's possible in children. So in Liz's study with Dan Hyde, they actually do get an effect with ordinal comparison. So I think it's possible that if we do it in our preschool sample using our task, for example, that just numerical comparison might work itself, and that would leave open this possibility that it's tuning the parietal system itself. And certainly in our monkey work, we're moving in the direction of, we're not finding a lot of numerical specificity in the untrained monkey. We're finding that neurons are representing all different kinds of quantity, and that actually the numerical readout is based on all of these different kinds of quantity information, it seems like, rather than just number selective cells. So I think that's an interesting open hypothesis that that there's something more general about parietal functioning that is being tuned by these various.
Yeah, I mean, there's some supporting evidence in the work of Karen Kadosh, where if you actually stimulate,
TMS, right?
do TMS stimulation,
Yeah.
not TMS, but you do electrical stimulation of some
Yeah.
kind. I mean, maybe it's
Battery to the head,
it's
essentially.
battery to the head, it could be
Yeah.
random noise stimulation,
Right.
which seems to speed up, if you like, the
Right,
tuning
arithmetic.
of the,
Yeah.
it makes it more effective. The training is more effective to
Right.
stimulate. And that would be consistent with my
The more general
rejected
parietal.
hypothesis.
Right. Yeah.
With, just, you've got a good, it's improving your parietal function.
So let's keep it